In this episode,
So we get a hell of a lot more defrost than even places like Scandinavia.
I do think I'm a good fan of the volumiser.
The house is the dog, the heat pump's the tail, and the tail should never wag the dog.
And it also depends how well your heat pump will modulate.
I think it's really difficult for the customer because I think they have got the hardest job.
Graunching or grinding is not what you want.
That's my favourite word.
We've all stuck it under the tunnel side.
welcome back to another episode of Homeowners Q&A. I'm your host Mars, and today we're tackling a topic that every homeowner should understand before installing a heat pump: how to get a well-designed heat pump system for your home. To unpack this, I'm joined by a panel of brilliant heat pump specialists. We've got Graeme Ross from Greystone Energy, Liam Riddex from Dex Renewables, Rob from Berridge Heating Design Consultants, Simon Murray from Optimus Heating, and Ken Bone from Renewables Suppliers. Welcome, everybody. But before we get stuck in, we'd like to extend a huge thank you to Greystone Energy for sponsoring this episode. With a stellar reputation for quality workmanship, Greystone Energy is one of Scotland's leading renewable energy specialists, offering full design, installation and maintenance services for biomass, heat pumps, solar thermal and solar PV systems. They pride themselves on delivering hassle-free end-to-end project management, ensuring homeowners and businesses get the best from their renewable heating systems. Greystone Energy work with Stiebel Altron, are Valent Advanced partners, and also work closely with Medea, reinforcing their expertise in delivering cutting-edge, high-performance solutions. If you're considering a renewable energy system for your home or business, be sure to check out Greystone Energy for expert advice, trusted installation, and ongoing support. Link in the description. Right, Rob, so we've spent a lot of time both on the Renewable Heating Hub website and on the podcast just trying to educate homeowners about the importance of getting a properly designed system. The one thing that now is coming up as a recurring question: what is a heat pump design?
A heat pump design is a completely different design to a standard traditional gas heating system, if you like. There are we're lucky in the sense that historically a lot of gas heating systems have been horrifically oversized, which actually makes them much more suited to lower temperature, higher flow systems. But essentially, it's a different beast with a heat pump. Very important that because we're now measuring actual heat loss from buildings, it's very important to get the mathematics right. And one of the biggest considerations to make when you're doing this. Gas is very forgiving. Heat pumps are not as forgiving when they're so much closer to the truth of the heat loss level, or the heat's actually an energy leaving that building which you're designing to replace.
So what factors are you taking into that design? Is it the pipe work? Is it the heat loss? What exactly goes into that design?
Well, the current building regulations now are stating that you must do a room-by-room heat loss calculation in order to ascertain exactly what the issues are with the building and how much energy that building is losing depending on the outside temperature, which fluctuates all the time. That's the dynamic movement of that energy changing. Once you design to your worst case scenario, which is your outside design temperature, which you get through degree days, which you can get online. For argument's sake, it works on various different postcodes, that sort of thing. But if you're designing to say -3 or something, you would actually design your heating system around that worst case scenario. So if for argument's sake it is 6 kilowatt or 5 kilowatt or whatever, mine's about 4.5 kilowatt in my house. That's what you design to. But then you need to make sure that you've got a appliance that you're going to be specifying for that particular project that can modulate down to its lowest output when the outside temperature is when SIBC state that you don't need heating, which is 15.5 degrees centigrade outside. So you've got to work very closely within those parameters to try and make it right. We have proven through Open Energy Monitor of late that oversizing of heat pumps doesn't present much of a problem as long as it's within a certain percentage, around sort of 20%, something like that. If you oversize it, it doesn't cause that much of a problem, because I think, as we've discussed here a few times, is keeping those compressors warm is very important for longevity and wear and tear of the actual units themselves. Gas boilers, yeah, massive problem oversizing. Heat pumps, you need to get those very close. There's two things that you can't oversize, as we've already discussed in this on various podcasts, which is expansion of the heating system and radiators. The larger the radiators you've got, the lower the flow temperatures you can go to, which clearly is the less joules of energy in real time that you're going to need to actually heat water up. So they're the big concerns. And obviously kilowatts and flow are completely joined at the hip. So pipe sizing and emitter sizing are crucial.
So Graeme, you obviously fit a lot of heat pumps. If you go into a property that's got an existing boiler, what do you look at in terms of this is what needs to be done. This is how I need to design it to make sure that this property actually stays warm.
The first thing that we start with is by doing a detailed room for room. That'll give you the heat required for that property. We then look at pipe sizing, see what's fitted, make sure you've got the right flow rate for the delta T. We tend to try and design to 40, so 40 degree, 45 degree is kind of our main aim of what we try and design to, and just get the heat pump running as low as you can, lower temperature as possible.
So do you advise on things like insulation? Because there might not be certain properties that might be able to get warmed up at 40 degrees. So do you then have to start looking at insulation to try and make that work?
It's not necessarily insulation, because like my old 1986 timber frame house has not been beefed up with any more insulation and can run at 38 degrees at -5. Yes, more insulation is keeps the heat in, less heat loss, but it's not a requirement to get an efficient heat pump.
So how do you actually get that to work though? Because we can run at 45 degrees at -2 outside and the house still feels cold.
That's just all down to the emitter sizing. The emitter sizing for that room just probably not big enough for running at that temperature.
Simon, you obviously go and see a lot of properties. What are the biggest mistakes that you see when it comes to heat pump design?
Obviously buffers where people just put a heat pump in where there's been like a combi boiler or a system boiler and they just haven't adapted the house. They've just slung a heat pump in, put a buffer there, got onto the pipes and walked away. So you can see like nice normal size house, 28mm primaries going into the buffer, and then directly on the other side of it straight down to 22, and you can tell there's like a fixed speed pump there, and there's no calculation really been done to look at that. And then other than that, the setup, I was at a project the other night, 3 houses exactly the same, identical, 7 kilowatts Valent heat pumps, all been built by the same builder. All 3 houses had problems. Went in, looked at the controller, and every controller was set up different. They were doing, one of them was on a heat curve of 0.8, and next door was on 1.2. He had his radiators closed, his strangling system volume. So small changes on those systems, and those heat pumps just start to work. It's just understanding how to commission and and a bit of system design.
So we have spoken about buffer tanks on this show multiple times. And the one thing that we've actually not covered, and it was actually raised by one of our followers called Manu422, so hi Manu. He basically asks, what exactly is the purpose of a buffer tank? So Ken, could you tell us what the purpose of a buffer tank actually is?
A buffer, we try and design them out as much as we possibly can. A customer that, no matter how many conversations we have with them, will want microzoning, then the buffer will be the safe space for a heat pump to work around. It's not ideal. We try, as I said, we try not to do it. We try and at least get about 50-60% of open loop in our systems, even with clients that want zoning. And it also adds to the volume of the system. But as we know, most heat pumps now have a PWM pump in them, and on the other side of the buffer is a fixed speed pump. And then so it might be right twice a day, 3 times a day, you might actually get the DT right. But 9 times out of 10, you've got a lot of distortion going on. So you will then eventually have to run the heat pump hotter and more or less efficient to actually get the end result out the other side.
So the question that we get from this particular homeowner is, and we see a lot of cases where installers are still adamant about fitting the buffers, and they keep saying that, well, the reason that we're putting them in is to actually help with defrost cycles. Are you saying that's completely unrequired? It's just a lame excuse and something that just should not be happening?
Yes, it is. If you can design it, so we work out that most of our open loop systems are between 120 and 140 litres of volume. So that's always open to the heat pump. So you are obviously on a slow and steady run, you're heating that fabric of the building, yourself and the system. So when it does then go into defrost, it robs a little bit back, takes about 5-6 minutes to do a defrost, and then off it goes again. When you don't have enough volume or the system's closed down, then that's when the heat pump will start potentially having problems, and you could get the defrost depth spiral and all sorts of things going on. We have a lot of problems with new builds in the winter where guys are trying to fire up the system. The house is stone cold, the slab is stone cold, the water in the underfloor is like 6-7 degrees, and the outside temperature is also very cold, but you haven't, there's no energy for the heat pump to get going. If it had a buffer, the buffer would still be at 6 degrees of water. So again, it still has no energy, but that's just a wintertime first start-up of especially new builds.
Liam, you're actually working with a homeowner that we both know in terms of trying to rectify quite an appallingly installed system. Their system has been suffering from a lot of defrosts, and they've also had a buffer. You've removed a lot of distribution pipes. You've actually done quite a lot of retrospective work on that. What was the issue with that particular system, especially through the constant defrost? So they had a buffer tank. The heat pump would still continuously go into defrost modes. What exactly have you seen with that system?
It was a Dakin unit into a buffer, and then out of the buffer was 6 manifolds with pumps on them, as well as then a hive circuit for a towel rail circuit controlled by hive that was also had a separate pump on that as well. So I think in total we removed 8 pumps, run it as open loop as possible, changed the buffer into a volumiser, and then just used the underfloor heating thermostats as limiting stats where possible, just to try and get it run as open loop as possible and more control for the customer, is what we did there. They have also experienced an issue with the unit, which is still ongoing, and we think it is potentially down to low refrigerant. So when it does get down to the colder weathers, it's just suffering itself.
So Rob, Ken touched on system volume. Could you just explain for the benefit of the viewers exactly why system volume is so important in a system, and what exactly is that system volume? Is it the full volume of water in the system, so radiators, underfloor, everywhere? Could you just explain that for us?
Water has got a very, very high specific heat capacity, about 4.183 at 55 degrees. It's incredibly hard to heat, one of the hardest substances known to man to heat. That's why we use it for cooling power stations and nuclear plants and all sorts of stuff like that. But once it's up to temperature, it's really easy to transport it around because we built pipes and we can do that. Because it holds its heat, the more volume of it that you've got, the more we can lower temperatures right the way down. So it's not like a very low water content gas boiler type thing where we used to be able to heat to sort of 70 or 80 degrees and run it around, where that heat would disperse into the room through the second law of thermodynamics. Hot will always go to cold. We're trying to get it down as low as we can, and I think we discussed this and touched this on this last time. The idea should be now to see what is the lowest flow temperatures we can get, because technically you could have a flow temperature of 21 degrees and still achieve 21 degrees in the room if you have enough volume of water to actually spread that around. Now, you need a hell of a lot of water to do that, and I'm just trying to work on a project at the moment of just trying to find out exactly what the Goldilocks zone is for different flow temperatures, and we'll stick within the norms of the best COPs that we're getting of, say, 30-degree flow temperature, 40-degree flow temperature, and up to maximum of 50-degree flow temperature, and see what the volumes are for that. But I think they're linearly linked, and I think that we can kind of prove that in an engineering fashion to get the best out of it. And it also does help with the volume of that, keeping the defrost cycles as well. But I'm not a big fan of buffers at all, because I think that you've got to, as Ken has just said, you've got to satisfy that battery storage before you're actually starting to get the heat to where you want it, which is in the radiators and in the rooms and into people's bones. But I'd much rather, if you have to get more volume into a system where you can't get larger emitter sizes or along those lines, I'd rather put a volumizer in. But I want to try and work on the idea of building a dynamic volumizer, so it bypasses the volumizer when when the return temperatures are low, but as the return temperature rises up, a dynamic SB diverter or something along those lines will divert it into a volumizer, lower the return temperature down, so you're keeping that delta T nice on the heat pump, getting longer run times, and you'd use the volumizer on that warmed up water as your defrost cycles as it reaches set point.
I'm playing with that at home, actually, Rob. Another thing is your design flow temperature, because obviously if your design flow temperature is higher in the DOT conditions, your unit's working harder, and because it's working harder, it will have more frequent defrost cycles.
And plus the fact, don't forget, we live in a temperate climate where we've got an average around 90% humidity, so we get a hell of a lot more defrost than even places like Scandinavia. And even though they're colder, their systems can work better than ours because they're not as humid, because they don't have the Gulf Stream.
Are you new to heat pumps and feeding lost? Then From Zero to Heat Pump Hero helps you understand, operate, and optimize your system. No jargon, just simple practical advice from one homeowner to another. Take control of your heating and save energy. Get your copy now. Link in the description. That's a very convenient place to segue into Volumiser. So we had a question on YouTube from a gentleman called Charles, and he's really confused about the positioning of the Volumiser because he's seen multiple different people basically disagreeing, saying some Volumiser should be on the flow, some people say Volumiser should be on the return. So Simon, flow or return?
So we like to put it on the flow. And the reason for that is obviously you've got nice warm water coming out of your heat pump, going into the heating system, stored in your volumizer. When that heat pump goes into defrost, it's taking water from the return side, and it's obviously naturally the pump's pulling water into your heating system. So you're still putting warmer water into the heating system. There is no right or wrong way of doing it, I don't think. Everyone's got a take on it, but that's ours.
Graeme Ross, flow or return?
We've always stuck it on the return side. I don't suppose there is a right or wrong. It's just, just one time following a manufacturer's diagram, stick it on the return, so we've always just stuck with that. But yeah, no, I'm a fan of them if there's not enough volume in the system, so you're not pulling heat out the actual property, and making the radiator stone cold. I do think I'm a good fan of the volumizer.
Ken, same question, flow or return?
We do, or I do return. Again, you don't actually need very high water temperatures to complete a defrost. I get what Simon was saying about he's preloading before it actually goes into the heating system. In my theory, logical brain, you're getting most of that defrost energy from the buffer or the volumizer, sorry, on the return. To complete that defrost, and then as the heating system comes back into play, then that volumizer will slowly warm up again with the return from the heating, and keeps your DT in check as well.
So we've got 2 returns, 1 flow. Liam?
I've always done it on the return as well. Yeah, I always done it just standard on the return. So I can see why you put it on the flow as well. So I can see both sides of it. I think some of the systems with like backup heaters involved as well, on the flow it makes more sense because then it stops that cold slug going back in potentially, so you can pre-warm that up. But I've always gone on the return.
And Rob Berridge.
Well, I'm going to throw a massive spanner in the works because I quite like doing that. I would say I'd rather be a little bit more agnostic about it because I can see the virtues on both sides. But I quite like the idea of a 3-pipe volumizer with a motorized valve on it for the defrosts, basically. So it's like if do you know what I mean? That to me, that you're going to get quicker defrosts and get the unit back in and get the heat to where it's needed. But I don't like loads of controls on heating systems, but in this instance, that kind of would work. But yeah, mine, traditionally I've put them on the return.
So there's something worth noting here as well. So we start designing at 35 degrees, and we're all open loop, so we just balance the underfloor circuit with rads. Interestingly, when you get to that temperature, you don't generally need volume because the size of the rads and the pipe work, you're actually satisfying the system volume. That whatever heat pump you put in, it's just going to work on the system itself rather than adding volume in.
I agree with that. So I would say a volumizer might be a bit more useful in the changeover months, but in the winter, I wouldn't say, because the whole circuit is running, the whole heating is running all the time, everything's open. I would say you actually don't need one when it's running in the winter at all, because you've got your volume within the system already.
The warmer months, as we go up that the curve, obviously we design at DOT. So where's the control around that as we get into springtime, and how do we know what the secondary side of the system is doing? How do we control that? So yeah, I totally agree.
I've kind of worked out that a 40 degree flow temperature to get 1 kilowatt is about 20 litres. So we're trying to work out what this Goldilocks zone is, and you know, there's loads of people we're debating it online all the time now, and I'm sort of tending to sway towards a little bit more of around 25 litres per kilowatt now from what other people that I've spoken to as well. So we're all learning, we're all trying to sort of, it's nothing's ever really settled with this. But if you can get 1 kilowatt at say 35 degree flow temperature, and that's 25 litres, it's very, very easy to build a system around that. And then if you don't have the volume, use that volume, but you're primarily using it for the longer run times and for the defrost. So it's just benefiting it from that thing. But I think a buffer or a volumizer, frankly, is just a bit of a trade-off regardless.
And it also depends how well your heat pump will modulate. Some heat pumps just don't like running lower than about 30 degree flow. So even if you are running low temp, in a colder day and said, well, I want you to run a 20, 27, 26 degree flow, they just don't like it. So they will cycle anyway because the compressor is too big. It just can't modulate down enough. Going back to the oversizing of heat pumps for the colder conditions, that's great, but I think there has to be a designed conversation with customers and particularly the manufacturer that you're picking, a line in the sand. Yeah, we can design the system to cover your lower ambient conditions, but it might have a back-on effect when the mild weather comes along.
My take on that is that if you've got a problem and it won't modulate down to that lowest point, as you're saying, what I've learned from a lot of manufacturers now is that as long as that compressor is warm, cycling is not so much of a problem, not like it would be with gas boilers. And we're going back to that whole adage of, when we were sort of coming to the end of the the big run of gas boilers, everyone's starting to learn all the mathematics on gas boilers. It was all about hydraulic separation and God knows what, and sticking in loads of plant that you don't need. In this situation, it's more it's completely the other way. It's kind of less is a lot more, in my opinion. But look at all of the Scandinavian countries of what they do. They don't do what we do, and we've seen through Open Energy Monitor that oversizing is not so much of a problem, and cycling is not much of a problem because the compressor is not in a uncomfortable zone at the end of the day. But they are sizing to sort of like 70, 75, 80% of outside design temperature loading, but they've got a much drier atmosphere than we've got. So they don't get as many defrosts, they get longer run times. So it's a completely different sort of kettle of fish, but they will rely on much more of a bivalent setup, so a hybrid setup in those countries, whether they're with heating up with a backup log burner or whatever for those sort of like 1 or 2 months of the year when it does get down below their point. I can see merit in both sides, but it's very, very difficult to kind of really know. It takes years and it changes at postcodes. That's the point. It changes where you are around the country.
I literally had a conversation about the cycling or the changeover month cycling, and I said exactly what you said, Rob. I said it's been on, the compressor's nice and warm. If it's 5 or 10 minutes before it comes on again, that compressor is still warm. The problem is if you're letting it off too long and the compressor gets stone cold, that's when you'll get a lot more wear and tear on that unit.
Well, it's the same driving a car, isn't it? All the damage of driving a car is done when you first started up in the morning. Once it's warm and the oils are warm around the car, that's it. It's you can start it up and stop it as many times as you like. It's no problem at all. So it's exactly the same with that. With any sort of engineering, graunching or grinding is not what you want. You want it nice and smooth, and that's the whole idea of long, low, and slow. And that's why all of us guys that are trying to enlighten ourselves on a daily basis are saying, like, right, volume, long, low, slow, lower temperatures, just let it run, let it simmer. It's just a simmering pot at the end of the day.
That's my favourite word.
I mean, my unit pretty much only stops for a defrost and that's it. It's just on constant throughout the winter. It's on constant.
Have you got the heat pump on a south-facing wall as opposed to a north-facing wall? Because I can see that this makes quite a difference.
It is behind the garage and it does face. It's kind of shuttered off, but it is south facing.
Well, I've seen some where they're placed in certain areas in the country where they're actually sitting in valleys, if you like, and certainly in Wales I see it quite a bit, and where the cold air comes down the valley, where it's so moistened. I mean, we're talking about 100% humidity sometimes in these places. It's very, very, very difficult to strike the right balance. But I certainly wouldn't want mine on a north facing in direct weather, something along those lines. I'd much rather it on a out of in the lee of weather where it's a slightly drier, more ambient temperature.
Mine's on a west facing aspect. So yeah, in the morning, no sun at all. And I must admit, I've been recently looking at the sensor on the back of the unit, and you can see it fluctuating when the unit's going on and off. So even though people say the air temperature is about the same, the air going across that sensor on the back of the unit, you're now getting wind chill. I'm now thinking that pretty much every heat pump should have a separate weather stat somewhere, and I think that may I don't know data, or I've seen a load of data to confirm this, but I do think other manufacturers that have that route of this is the outside sensor, you need to put it on the north facing wall, that has no influence with that wind chill being generated by the heat pump itself, I think there's energy efficiencies to be gained there.
I think that's absolutely spot on. And you know what, we do it with other weather compensation controllers, don't we? It's always on the north side under a building soffit board or something like that. So it's out of any direct wind or any direct rain or anything like any other influence at all. It's in that ambient position. So it's just taking the air temperature at that point. And of course, the humidity is slightly less when it's up at that height than it is right down at ground level.
I think it's important we should point out here that what we're talking about is really fine-tuning systems. For clients that watch this back, it's way more important for your system design inside the house than what we're talking about now, because some clients just won't have the option to where they position that heat pump. It will just need to go where it needs to go due to building regs or the house or whatever. This is really fine-tuning your heat pump to work at super efficiencies. The most important thing in the design is what's going on in the house. The house is the dog, the heat pump's the tail, and the tail should never wag the dog.
I would still say that positioning could make the difference between 20 or 30 pence a day.
Sure, but if you're in a terrace house and you haven't got a choice, then I don't want clients to start getting beaten up on, oh, this is not the right thing to do. It's important that they know they can still get a really good install wherever that heat pump is placed outside.
So, Liam, we've got a question off the forums, and the homeowner asked, how critical is pipe sizing when it comes to heat pump efficiency?
Very. I think there's sort of like a sequence you have to take when you go to a site, and I think as we've covered, the first thing's heat loss. Once you've got that, you can then sort of build the rest around that. Emitter size and pipes, they all come hand in hand. So yeah, it's very crucial. It's one of the main points. The heat loss needs to be done correctly first, not as an estimate, but like you said, a room by room heat loss, and then you start building it from there to your other sort of steps. So you look at like emitter size and pipe size, and they all come hand in hand.
So, Graeme, just walk us through a system. So somebody's got a lot of microbore in their property, and we've been speaking about volume and actually designing an open loop system and trying to distribute that water evenly through the microbore. Is it possible to do quite efficiently in an open loop system if you have got pipework that's kind of narrows in different places throughout the property?
Yeah, as long as your main primaries are fine, and as long, I mean, you can normally get about a kilowatt of heat down 10 mil. It is possible, as long as the emitters aren't, again, like too big, and the heat that you're trying to get through that 10 mil isn't too great. We've got two systems that we fitted last year, both performing well, both on 10 mil microbore to the radiators. I think it's a bit of a myth that it has to be 15 mil. Obviously, you start going up heat pump sizes, the more volume you've got, then yes, the bigger pipe sizes do help with the volume and the flow rate that you require. But no, I think they do work fine on, and they can still be efficient and still achieve over efficiency of like 400.
What I've come across in my years is a lot of heat pumps are fitted in the summer or when the weather's good, and because they may have not checked, designed, redone some of the pipe work, that heat pump, let's call it a 10 kilowatt, because it's in the milder weather, that unit's only running at 5 kilowatts. And at that time, at that moment in time, the existing pipe work might actually be okay. It's only when we start getting into the real colder weather where the heat pump's now working, the velocity's now picking up, trying to get that energy through the pipe work and to those radiators. The radiators might have actually been changed, but if the pipe work feeding those radiators can't get that energy to them, that's then a spiral of chaos and inefficiencies. So people say, yeah, it works fine in the mild weather, but as soon as winter comes along, it doesn't work. Alarm bells will start ringing. Getting that energy, you need to get that energy to that radiator or underfloor system based on the worst condition possible, design condition, and maybe a little bit more, to make sure that when that unit is running flat out, trying to deliver those 10 kilowatts, the pipework circuitry can carry it.
This is all about resistance to flow at the end of the day. It's all about how many pascals that you're trying to get over per meter of resistance within the pipework. I mean, SIPSI state between 300 and 500 pascals per meter, but if you've only got a short run, let's say you're coming off a main flow and return, you've only got a short run of 8 or 10 millimeter pipe or something like that, and it's 2 meters there and 2 meters back, then that's 4 meters. If you've got 600 pascals of resistance per meter, that's only 2,400 pascals at that point in time. When you think your smallest pump that you can buy is like 50,000 pascals, you know, that's when you start to add it up, and you've got to make that engineering decision of whether you start ripping floors up and charging the customer a lot of money to upsize pipe work, or whether you can actually get away from it. But the one thing that really kind of gets me, and is normally the thing that people don't understand about calculating the index circuit for this at outside design temperature, is like pressure independent valves, like some of the thermostatic radiator valves that are on supposedly, well, open loop systems, and they're not open loop when they're like that. So you need to be looking at the if you're going to put a TRV on there, it needs to have, you know, really good high kV rating on it, so a nice high flow running right the way through it, so you've got least resistance as possible. There'll be no resistance in the radiator at all, but it's those considerations if you're coming across Microbore. And the other thing that I'd always be worried about as well with Microbore is that very few people that installed it actually used a proper pipe bender when they did it. They just put it over their knee, so you can get quite a bit of kinking and all sorts of things going on, which is a bit of a problem. So unless you can see it in its entirety, yeah, you got to make an engineering decision really. But yeah, it's all added cost, isn't it?
You're right there, Rob. Going back to the TRV thing, I mean, if your system's been designed, you know, 100% of the fabric, and now you're putting in radiators that match 100% of that room, in theory, you don't even need a TRV. But we put them in because the clients, even though you may have designed that bedroom, we look at a whole house approach, 21 degrees. So a lot of people don't want their bedrooms at 21 degrees, but I'm in my office today. I want my office a bit warmer. So on a commissioning basis, everything needs to be fully open, absolutely fully open. Run it for a week, a couple of weeks. Try and trim, get the weather compensation trimmed. Again, that's whatever you're doing in the milder weather, you might still have to play around with it when the cold weather comes along.
I agree. I mean, I only ever put hydronic balancing on rooms with solar gain. Everything else now is just completely open, because you just don't need it. We've got really good compensation controls now, and I know this really winds you up, Ken, because I've seen you get like this quite a few times. Is that compensation controls have been out probably around 20 odd years, maybe even longer than that, you know, and why we haven't taken advantage of them in the past, I have literally no idea. It's really bugs me as well. So
I agree, they're brilliant. I just think if every heat pump had a combination of weather compensation and room influence, I think that would be in a whole picture heat pump thing. I think that would be the next best level that we need. That's why you've got people like Havenwise, Homely, that are trying to fill that slot. The customer, even you could have a weather compensation that's overstated, over compensating, and you can still have too warm a house. And customers, the point we have is trying to get a customer to make their own judgment and start trimming the settings. It's very difficult.
this is something that the end users really kind of need to consider when they're getting quotations in for a lot of these projects to come through. That speak to your installers about what the compensation control strategy is, and what you expect, you know, and the fact that you now know that the lower the flow temperatures you can get, the better. But again, what, as Ken said, what that unit is going to run at its sweet spot in, because a lot of units don't like to run lower than say 25 degrees flow temperature or 29 degrees flow temperature. Those sorts of considerations, there is quite a lot to think about. But when I meet somebody to come to do some work for me on, you know, one of my motorbikes or whatever it is that they're doing, I go a lot with my gut feeling. I look at them, I look them in the eye, I get to understand, I get to know them. And, you know, if you're lucky enough to find a good engineer these days, please hold on to them, because they're hard to find.
I think it's really difficult for the customer, because I think they have got the hardest job. They get, you know, they get 4 quotes, as you would, and then they all come back and they're all different units, different sizes, different prices, and then the home admin has got to go, well, what do I do here then? And I think, yeah, just ask some questions, you know, ask to see their previous work, see if you can speak to some of their existing customers as well. So I think most people are more than happy for you to do that, and sort of take it from there. But yeah, I agree. Just, yeah, definitely ask the questions.
Are you thinking about getting a heat pump? Then don't get caught out by a bad installation. Bodge Buster is your essential guide to asking the right questions and spotting red flags before it's too late. Written from real homeowner experience, this book gives you the knowledge to avoid costly mistakes and make informed decisions. Get Bodge Buster today in print or for Kindle, link in the description. Yeah, could you just expand on that? Because I was actually going to get into this in a second, but you get your heat loss calculation, and then that basically determines the size of heat pump in terms of kilowatt size that you'll actually need for that property. Those data sheets that the heat pump suppliers often provide don't always match up to those conditions. So how do you factor that into the equation?
We've noticed that with a couple of units at the moment, what they're saying they can output and what we're seeing on open energy monitors, two completely different things, which again, it's really difficult for an installer to sort of factor that in, because obviously we're going off a data sheet from the manufacturer, so you sort of trust that. What I find difficult is trying to get the information out of a manual is really hard. So, residual pump head, that should be something that's quite obvious in a manual, but it's always, sometimes it's not even in there. You have to call the manufacturer and you can't even get that. So I think it is different. We need manufacturers to be a bit more open with some of that stuff that we can use to make an efficient system. With the output charts, again, I don't know how we sort that. It's just we sort of hope that they'll be correct when we look at them, I guess.
It's difficult for both people, isn't it, Simon, in terms of both the homeowner and the installer in that case, because if you've not installed a particular brand before and you deliver a 9 kilowatts heat pump for that system, for that property, and it just never delivers, it makes you look stupid, and the homeowner gets irritated, and it seems nobody's at fault but the actual manufacturer.
I totally agree. And you need to know your kit. You have to have that close relationship with the manufacturer. We only fit 2 heat pumps. We have very, very close relationships with both of the heat pumps that we fit. We know the kit inside out. But that's one of the problems for a client. When someone goes to sell them a heat pump, they think a heat pump is just a heat pump, and all heat pumps are not equal. There is so much variation between brands and what they do. And okay, there are cost differences between different units, but actually if you go for a cheaper option, you end up paying more money in the long run by installing that unit. And we try and get this message over to clients. It's quite difficult because heat pump installs aren't cheap, especially when you use the better units and you're looking at the house and you're redesigning pipe work and you're going down that road. But yeah, the client pays anyway. You will pay, and your heat pump will potentially not last as long.
I use a few analogies on my training courses, like you've got a typical house in the south of England. It's in an urban environment. It's not being windshield. The DOT is -2, -3. So you pick up a 10 kilowatt heat pump for that area. You then take that house and you put it on a hillside in Scotland. It's the same house, but the conditions are totally different. I mean, go back to Rob's analogy about the story about the pocket valley. So you could potentially lose 1 to 2 kilowatts with frequent defrost cycles, but on paper or whatever, hopefully the manufacturers are actually true in what their drop-offs or their capacity is at certain ambient conditions. But it doesn't say if the moisture content or the humidity is at this point, it's going to do X, or if it's a dry winter, it's going to do Y. So yeah, trying to get as much it's the same as heat loss, doing a heat loss, trying to get as much information from that client. Hopefully they've lived in that house a long time, they've lived in that area a long time. Listen to what they say, listen to how their winters are. 3 miles down the road, they don't seem to get any snow, but we seem to get all the snow, that sort of thing. As an engineer and with the client, try and do a compromise. Okay, we're going to push that DOT a little bit more. And so the radiator is now going to be a bit bigger. Maybe we need to potentially go to a net size heat pump for that circumstance, that individual, not what's happening to the house 3 miles down the road. And that just comes with experience. And unfortunately, we make mistakes, but we learn by our mistakes.
The battle with the technology of a heat pump maybe not being exactly what the data badge says on the tin. If you're designing at lower flow temperatures and you're saying like we do at 35 degrees, you've got so much scope to go up on that heat pump. If you put the right system in for it to work, okay. Also, heat loss is subjective. U values are written in a book, right? Specifically design guide. We're told what the rate of energy is or the time that it leaves a property. That probably isn't right. There'll be variances across all of that stuff. So while we're still doing heat loss surveys, everything about your install is subjective. So what we need to do is get the right system. This is why the system's so important, because then we have so much room to work with the heat pump, and we can maneuver the heat pump to work for that home. Quite a lot of the time we're finding when we're doing a 45 degree install, because some houses just can't have a 35 degree one, radiators don't work, rooms too small, we're finding the house, okay, it comes out in the heat loss, it's 45 degrees, but when we're actually running it, and we're running it at design temperature, actually it's more like a 40 degree flow temperature unit.
I designed mine to 40, and where I live, I'm DOT, it's minus 4.3. And when I did the calculation, I said, I've got insulation on the floor, I've not done it yet. The heat curve runs at, I've got it right down to 0.4, and it'll happily provide 20 degrees in the house, minus 6 outside, and it's not even hit 40 degree flow, it's probably like 36 to 38. So I think they are a bit over-egged with the calculations.
I tend to, after the heat loss, I will look at the worst room and see how practicable and physical a radiator could be of that room, and then that would then maybe dictate the rest of the rad sizing or underfloor heat sizing in the rest of the house, because that's the room you've got to heat. I know what Simon's saying, that's great that he's doing systems at 35 degrees, brilliant. But if that room needs a 3-meter radiator at 45 degrees, hopefully not, but if it did, unfortunately, that might then dictate what everything else goes. You can change the delta T of that one particular radiator, and we'll go back to balancing. So potentially we could get more energy in because we're slowing down or increasing the DT of that radiator. But obviously we're trying to make it a simple installation for everybody and to roll it out to mass market and everything else. You can play with the figures sometimes, but I normally pick the worst room as a starting point, and whatever physical practical size I could get an emitter in there will make it run for the rest of the house.
So there's another element to this that no one's touched on yet, and as a business, we're not Scott chasers. We have a vision that we imagine when we're putting a heat pump into someone's house, obviously in that city, let's say, not many people, total populace, will have heat pumps. We then imagine overnight that everyone gets a heat pump. Now, the install that we're giving our clients, what we're doing is we're future-proofing them against grid loading, because, okay, at lower temperatures, your heat pump's working less, your draw is less. We have a bigger thing coming down the road in sort of 5-10 years where mass adoption of heat pumps has taken place, and it will. And all of a sudden, all these 300% heat pumps, I'm sure no one does those here, but all those 300% heat pumps are all of a sudden a massive problem and are creating problems for that localized grid.
It's a real beef for mine. The heat pumps are going to melt the grid when we can fit 9 kilowatt showers and induction hobs without informing with DNO and stuff like that.
I think supply of energy is a huge subject, probably not for this sort of podcast, but it's a massive consideration. And I don't know, from what I was reading, I think a lot of the DNOs now, I mean, I've seen a greater number of them actually saying, well, hang on a second, this is going to have to go to appeal, or it's going to have to go something along these lines. And that's a bit more of a worry, and it makes you think to yourself, well, how close are we to this cut-off point of actually having enough energy or not having enough energy as we're trying to push this transition forward?
We had one where we were told that we could install while they were doing an inspection, no problem. And then we had the DNO come back to us 6 months later, telling us that this heat pump was impacting the harmonics of the local grid, and they wanted to charge us £27,000 to put that right. We had it in writing and we won because we do everything on point. These are the challenges that we're facing.
So, Graeme, a short while ago, Rob mentioned the index circuit. Could you just explain to viewers what an index circuit is and why it's important?
It's just the worst performing part of the system. So you've got to design to that index circuit. Once, if you've got the head to cover that index circuit, the rest of the system on the design will be fine. That's a circuit you need to overcome.
So how do you design for that? Is it just a matter of figuring out kind of pump size, speed? I mean, how do you factor that? How do you work it out?
Just through calculation. Just need to work it out through the calculation. Just to work out if the pump has enough head to get over the resistance of that circuit.
And is that possible to do even if you don't know what the pipework is inside the walls, if you've never seen it before?
You can generally find out piping because you'll see it from like either, if you get access under a floor, you'll see it in an architect. You can trace pipework out. You'll know what a bit of pipework is just through experience of installing. So you'll be able to trace all the pipework out. The only times that you really can't is if you've got these nice floating floors with battens and finished floor surfaces on top. But the majority of the time, there's not any problem where, like even if you do need to upgrade a bit of pipe, you can normally do it. I mean, we don't come across many houses that are solid floors, or like our type of houses tend to be like they've got a solar and you can get underneath the floor, you can do upgrades. You just want to design everything so it can run it as most efficient.
If your index circuit is really poor, it might be only a little bit out. So actually upgrading that spine pipework or upgrading your primaries can then gain you head pressure to get over that resistance to the worst index side of things.
The index circuit is basically it's the largest resistance to flow of any component within a heating system. So whether that's a circuit, whether it's a valve, 9 times out of 10 it's a valve, it's not anything else. And all you've got to do is just overcome the flow of that to the delta T that you want. And then this is where you've got to do a trade-off. And on most domestic buildings, I very, very rarely see an index circuit over 20 kPa, which is 2 meters of head. And the smallest pumps you can get are 40 kPa or 50 kPa. Pumps are a big thing, and a lot of even ERP, which is the performance on pumps, is outdated now. And as far as I'm concerned, all pumps should be either delta T regular controlled or delta P controlled. One of those two. Delta P would be the pressure in kPa of what they've got to get over of that calculated index circuit. But the amount of times that I actually see the index circuit on a system is actually not the system itself. Often it's the heat exchanger within the actual unit itself that's got a higher kPa rating than anything else. So you get a lot of heat pumps that come out, and you might have an index circuit of say 20 kPa, but they've actually got 120 kPa pump sitting inside the unit. So, loads and loads of residual head there, which is there sitting there, frankly, over pumping. I mean, there's a horrible statistic. I know I keep coming out with it, but there's a horrible statistic which I believe is quite true. And that's between 15 and 20% of the world's entire electrical energy usage is taken up by dead-headed or oversized pumps. I mean, think about it for a minute. That's trillions and trillions of pounds, isn't it, of wasted energy?
We need that pump head to get around those buffers.
That's it.
Yeah. Put at least 3 on, just in case.
No one seems to know how to size them. People, I remember doing training courses and saying, "So how do you size a pump?" And the amount of people that come back and say, "Well, you look at the height of the building, and then that's the." It's just nothing to do with that at all. Absolutely nothing to do with that.
What goes up must come back down.
Exactly that. But I design. I might get a few groans here from some of you diehards, but I quite like designing certainly open loop systems on one pipe circuits. I think they work absolutely brilliant. I've done a few in churches and swimming pools and that sort of thing, and they work an absolute treat on open loop systems. They really do. And there's no resistance on any of those at all. It's just it's so tiny. And people, when you specify a pump and the engineer comes in and looks at it and says, "No, that's never going to work," and you say, "Look, well, there's the maths. It does do it." So I think pumps and residual head are something that we really start to need to focus on as well in this fight for efficiency that we're trying to do.
I'm terrible. If I go around to do an audit on an old existing property, I pull pump plugs all the time on manifolds and wait for the phone call, but the phone call never comes.
No, it never comes. No, this is it. Yeah. Do you know those figures? That 15 to 20% might be right. It might be worse than that. I don't know, but it's that's what I was told. That's an awful lot of money, an awful lot of waste.
So, Liam, on the forums, we're beginning to see more and more cases where people have taken ownership of new homes, and there's a ton of on-off stats in these properties which are wreaking havoc with these systems. What is the simplest piece of advice that you can actually give to a homeowner to try and overcome some of these issues that they've got because they've just got so many of these on-off stats?
The ones we see the most is where you've got a mixture of controls. You've got underfloor heating thermostats running pump packs, and then you've obviously got whatever other controls you've got as well from the heat pump, either on off, or sometimes you ain't got another tower or circuit with another stat on it as well. So it all depends sort of what unit you've got. Try and dial in your weather curve as much as possible. Put it on weather compensation, and then just use your stats as whack them up. You're not going to close that down. Just use them as limiting stats if you can on underfloor. A lot of jobs we go to and we do, everyone loves glass. And the one thing we can't control is the solar gain. So that's where the limiting stats do sort of come in and help. But yeah, just get it set up on weather compensation and whack the other stats up. Is my best advice on that.
I've recently been to 2 jobs. One was a ground source in a new build. One was an older property with a air source. Both high running costs, poor control. So the air source went in, it was on-off control. Micro-zoned everywhere. So I pulled all the heads off the manifold, put it on weather control, and about a week later he says the house is now warm and it's costing me cheaper to run. Same with the ground source. I went in and not seen the job before. The unit wasn't on weather compensation at all. was on-off control. So put it onto WeatherComp, disabled the on-off, again went around the whole house. I loosened all the actuators. I didn't take them all off. Their systems never worked correctly in 2.5 years since they've been there. 3 days later, she says the house is 23 degrees now. I need to turn it down. So, which I assisted her on the phone to do. She was quite savvy, actually. She'd already been changing components on the ground source. I'm not going to mention names, but she'd already been quite savvy. So hopefully we can get that weather compensation done down, and then going back to what Liam said, any rooms that then are overheating compared to the rest of the house, you would potentially put the actuator back on that particular room so they got a bit more control. We don't know what those installers originally did. Yes, we might have a set of plans of the underfloor. When you're going after somebody else's work, it's very difficult to go in and say, actually, I think it's all a bag of whatever and it all needs ripping out. We've got to try and help the end user to get to the best point that they can with that system by opening the system fully up onto weather compensation and running that for a little bit of time, then gave me some feedback data to make judgments in what to do next.
I'd have a message for all the end users, and that is that you don't have to be an engineer, you don't have to be anything like that. But this new system that you're putting in, this heat pump system that you're putting in, is an investment. We've got to start looking at this as an investment. We've got to start with, in this country, be proud of the heating system that you've got. I mean, I go to friends and family in Germany and stuff. They can't wait to show me their plant rooms and various other things like that. Whereas in this country, we see heating as a kind of rather an inconvenient necessity, and it's just it's a bit of a cultural thing, which is a bit sad. Be proud of what you've got. Ask plenty of questions and educate yourself on some of this idea that low temperature heating is low temperature heating. Rads don't have to be hot. As long as you're not cold, then it's working and it's working fine. If you're not getting, frankly, now on a system, if you're not getting over sort of 3.5 COP on your system, I would suggest you've got a design issue somewhere along the line there and you need to sort something out.
If you've got any questions about heat pumps, then you need to join the Renewable Heating Hub forums. You can connect with other homeowners, share experiences, and get advice on heat pumps and renewables. Sign up today and be a part of the conversation. Link in the description. So that's a wrap for today's episode. A huge thank you to Graeme, Liam, Ken, Rob, and Simon for sharing their expertise in helping homeowners understand what a properly designed heat pump system actually looks like. Too often, heat pumps underperform due to poor system design, so knowing what to ask your installer and what to expect from a well-thought-through system is key to getting reliable performance and efficiency. And a special thank you to Greystone Energy for sponsoring this episode. If you're looking for expert advice, design, and installation of renewable heating systems in Scotland, be sure to check them out. Link in the description. If you enjoyed this discussion, hit like and subscribe for more episodes helping homeowners make informed decisions about renewable heating. As always, stay warm, stay green, stay tuned. Goodbye.